now have a sort of new circuit mode of operation that exhibits itself under these conditions. Formerly we had voltage rises on 1, 2, and 2-3 of 8 volts apiece. This is shifted to a stronger voltage. The whole system is shifted to a more 180 phase relationship, leaving the remaining 1-3 and 1-2 voltages at a minimal value. So we have one strong point of interphasal voltage in this system as it is acting now. We have 0.3 volts enabling 3.9 volts on the first resonant rise. Phase 1. Phase 2, we have a full volt enabling 4 and enabling 7.7 volts, Q 7.7. And on the third phase we have 0.4 volts enabling 4.26 volts, Q of 10. That describes the voltage side of the system. Over here now we're going to look at the amperage side of the system. And of course we've mentioned we have a recurrent problem in this circuit, and that 2 of the stator lines, phase 1 at 0.14 and phase 2 at 0.311 to 308 fluctuating, those are supposed to add up to the center meter stator line serving phases 1 and 2, reading 0.68 at a stable value. And we notice that stator line 1-3 is at a low value of 0.11. So let us say then there's a roughly a 6-to-1 ratio of current right now being exhibited on them stator lines to serve those loads. What we're going to do then is observe that ratio now when the 5-volt field is employed. Now we see that the ratios have totally changed. We have near 2 amps on the left stator line 1-3, and we got 2.8 or 3. So we got 2/3 the amount in the center now. Before we had 6 times the amount. And then the actions of current delivery on the phases, they're all showing themselves near 1 amp on this functioning. Now that means then, of course, then since those ratios have changed, our voltage ratios on the other side should have changed. But nevertheless, that's leveled out there. We have demonstrated that. Now we want to go on to the scopings. We're going to turn the field back off again. But we do need to mention the fact, well, we can do this with the full field. Right now we're at 2 volts per division. And we got 0.8, 0.9 amps. A very fluctuating amperage on those phases there. We also have a scope here with a sensor on one of them phases. We can see that even though the amperage in the system is fluctuating quite a bit, scoping is not, amplitude-wise anyway. We're going to go ahead and turn off the field to make these observations, but we'll note that those ratios, this is a different process that we're studying without the field, obviously. But we're back to where we were with point 14, point 3, and point 15 on phases 1, 2, and 3. Phases 1, 2, and 3 are represented by white. Right now we got a sensor over phase 1, the white one. It looks like our sensor's at 1 volt per division on our delivery. We have a 1 volt input from stator voltage 2 being magnified to 8.1 volts, and that's the sensor is on that coil, and it's producing 0.146 amps on the top layer. Underneath that layer, of course, we don't know what's under that layer. Phase 2 probably. And we have our scoping. Dear me. It's getting hard to do all this. Okay. We're going to turn our scoping magnitude up on that channel. .5 volts. We're going to move the sensor. Another amplitude of 2 divisions. Sorry folks, that's on the bottom sensor. That's starting out right. Okay, we got the exterior coil. That's our coil sensor. Now we're going to move that on to the top poles of the 666 system. Currently consuming 0.14 on the first test, 0.30 on the second, 0.314 on the second test, and 0.15 on the third test. Here goes the first test. We got almost 2 divisions there on the scoping. We're going to go, that's the first test on the 0.14 amp current on the top layer. Now the second test will be the 0.319 amp on its top layer. And as we see when we did these tests, the volume of that magnetic field didn't seem to change on the sensor, even though there's more amperage on that top layer. Okay, now we're going to go to the third coil, phase 3, top layer, 0.15 amps. We find that 0.3's magnetic field on its pole face is totally wiped out. It's not totally wiped out, but it yields a non-sinusoidal signal. And what we did is we got the other channel on the bottom of that wafering, and now we can look at the channel 1 and channel 2 addition. Volts. That's with 0.5 volts on each channel. The signal from the reduced signal is very cyclic. It's got the influence of the 1/6 harmonic on that. Now let's look at that. As we can see, that's a different non-sinusoidal signal coming from that pole area, and it's far less in magnitude than the strong sinusoidal signal coming out the other end. So if we want to show it in equal magnitudes, we show the scoping as thus. Now, more importantly, we're going to change a few more things. We're going to take that dual channel observation and we're going to compare the strong pole, its phasing in time, with regard to the other strong pole's phasings in time. And to do this, we're going to take the coil now recording the weak pole on phase 3. We're going to move that to the strong pole upward facing on phase 1 and phase 2. Here we go to phase 1. You see that when we went from phase 1, the scoping shows that it was in phase, and we'll try that again real quick. That's showing that those two strong poles in time are coming out simultaneously. And then finally we'll move it to the third coil, phase 2. And we see that that one is opposite. So we have, in a sense, we have that strong pole, that this signal here is from the bottom coil, and it's identical to the top phase 1 signal. We've already seen that it's not identical to phase 2. So then, to conclude this experiment at least, what we want to do now is compare phase 1 and phase 2 itself on the dual channel observation, and which we should suspect that formerly those two positions in time and space have yielded identical results, that once we do this, it should remain opposite. We shall then go and take the bottom coil out of phase 3 stack and place it on top of phase 1 to record that observation. And as we can see, those fields are identical. And so what we can conclude here is what we just showed, the phenomenon of three opposites in time. Now, having dismissed all that, we're going to look at the inductor, secondary inductor. It's off to the side in space. We're going to put that inductor on one of the phases. We can put it right over the scoping, as a matter of fact. We're now pulling 218 volts from that top coil in resonance, 28 some milliamps. But look how the scoping changed. Quite a different picture there. And similarly there, our amperage input for phase 2 went down to 0.22 amps. Well, I don't know if it went down that much. Let's go and take the intervening sensor. We're going to take that intervening sensor off and let the secondary coil be directly over phase 2's higher amperage, formerly 0.30 some amps. And paradoxically, we're receiving, I think I recall, we might be receiving less voltage now when our proximity of our phase increased, and our scoping looks like that. And we lift that scope indicator off of there real quick to see what happens. Now we're just picking up the fluctuations on the signal of the channel. That goes back, the repercussions are on our new power input. We have 0.12 amps on phase 2 and 0.10 on phase 1. And there's the reaction of drawing off of phase 2 on phase 1, showing on the scope. And we'll call this one quits for now.